and welcome to another homework helper video for section 5.4. In this section we're learning about the fundamental theorem of calculus, which is meant to make our lives a whole lot easier. So instead of doing this limit process for finding the area under the curve, which we found to be a little bit tedious, now we can just use this fundamental theorem, and that theorem says that if you're evaluating an integral from a to b of some function f of x dx, then all you have to do is, if you can find the antiderivative of a function, evaluate that antiderivative at b, and evaluate it at a, and subtract those two, and you will get the area under the curve, right? So this is our fundamental theorem, and we can use this. I just want to walk you through this first one to show you how to use that theorem a little bit. So we're given this first integral. First thing I'm going to do with this integral is I'm going to simplify this a little bit. I'm going to change it to the integral from 5 to 8 of x to the negative 2 minus 1 dx. That just makes our lives a little bit easier. And now from there, what you can do here, I'm going to erase this now that we have figured that out. Ooh, maybe I don't want to erase my 5. Well, maybe I will and just write it back in again. And here we go. 5. There it is. Now, the next step I'm going to do is I'm just going to do the power rule on that function, right? I can find the antiderivative of this function with the new rules. So what we do there is we just say, okay, what I've got is raise the exponent by 1, x to the negative 1, divide by that new exponent, right? And for negative 1's a constant, so it becomes negative 1 x to the first. The idea for that term is, keep in mind, whenever you do these, you can do the derivative to make sure you'd get back to what you started with, and that's definitely the case for both of these. Both of those terms there. So what we've got here is we want to evaluate that from 5 to 8. So now I have a function. This is my antiderivative function. Maybe I'll simplify that. At negative 1, x to the negative 1 over negative 1. I don't like how that's written, so I'm going to change that a little bit. It's just negative 1 over x is all that means, right? Minus x. That looks much better. And we're doing that from 5 to 8. And so this is my antiderivative of the original function, right? That's my antiderivative. Now all I have to do is evaluate that at 8 and subtract what I get when I evaluate it at 5, and I should have my area under the curve. So putting 8 into that function, I get negative 1 over 8 minus 8 minus, put 5 into the function, I get negative 1/5 minus 5. Probably the thing that people will trip up the most in these problems is all the negative signs going on there. That sometimes will give people fits, but you got negative 1/8 minus 8 plus 1/5 plus 5. And I'm going to cheat a little bit. I could do the common denominator and add those all together, but why not use this trusty calculator that I've got? Negative 1/8 minus 8 plus 5 plus 1/5. Not necessarily in that order, but math. Fraction, to make it write it as a fraction, what I end up with there when I evaluate this is negative 117 over 40. Okay, so keep in mind, the reason this is negative is because the function that we're talking about dips beneath the x-axis in between 5 and 8, so it's going to have a negative value. But there you go. That's the value of our definite integral using that fundamental theorem of calculus. The next problem I wanted to go over is all about this average value. And I want you to keep in mind that this section also talks about the mean value theorem for integrals, and you definitely want to go through that. But I just wanted to show you in this section that mean value theorem and the definition of the average value are very related. They're very similar. So if you look at this formula for what they call the mean value theorem, so there's some value of c such that this integral will be equal to it here. It's all about rectangles, and you can watch my short little video on how those rectangles are related to each other and all that good stuff. But what I want you to keep in mind for sure is that these formulas are really the same thing. If you think of solving this equation right here for f of c, right? So in other words, I'm going to rewrite it just a little bit differently. Put the f of c times b minus a on the left-hand side of the equation instead of the right-hand side. If you look at this, and if you want to solve this formula or this equation for f of c, you would divide both sides by b minus a, or multiply by 1 over b minus a, right? Same thing. So you'd get that f of c is equal to 1 over b minus a times the integral from a to b of f of x dx, which is exactly, this right here is exactly what they put in the formula for the average value. So in other words, if this f of c exists, it is the average value of the function. In other words, the average height of the function in between a and b. All right? So that's what we're doing here. We're trying to calculate what the average height of this function is between the two values. On this interval, what's the average of it? And keep in mind, that's not as simple of a question as it seems it could be, right? Because to usually define the average, what you'd have to do is add up all the heights of the function and divide by how many there are. But keep in mind, this function is continuous. It's not discrete, right? So there are infinitely many values, infinitely many heights of this function from -2 to 2. And then you'd have to divide by, well, that doesn't even make sense the way we traditionally do a mean or an average, right? So that's the idea here, is this gives us a way to find an average value of a function given that there are infinitely many data points on the function, right? Because it's continuous. All right, good. So I'm going to delete this. I'm going to delete everything I've done so far, actually, so we can actually answer this question. I just wanted to talk a little bit about how similar the mean value theorem is, and the formula in the mean value theorem, and the formula for the average value, and how they're related. But this question is asking about the average value of a function, so let's jump in there. To find the average value, all you really have to do is use this formula, right? I'm going to be calculating 1 over b minus a times the integral from a to b of f of x dx. Okay, so just using that formula, remembering that b is the endpoint of our interval, 2, and a is the other endpoint, the left endpoint of -2, and we're just plugging those two numbers in here. The function I'm talking about, the function in question, is 4 minus x squared dx. Of course, this part is relatively simple. It's 1 over 4. Now I'm going to do the antiderivative of my function. Antiderivative of 4 is just 4x. Antiderivative of x squared is just x cubed over 3. And I'm going to use my nice fundamental theorem of calculus to go ahead and evaluate that antiderivative at my two bounds here. So I'll plug in 2. 2 times 4 is 8. Minus 2 cubed is 8, so 8 over 3. Just want to be careful. I always put these in parentheses, even if I don't need them, just to make sure I do all the negative signs right? So it's f of b minus f of a. So when you plug -2 in, you get -8. -2 in here, you get -8, but I'm going to add it because it's a negative here, and -2 cubed would also be -8. So it's minus -8 or just plus 8 over 3. And whatever that's equal to, right, will give me my nice average value of this function. So 1/4 times, oh goodness, I don't know. This is what the calculator is for. What would I get here? 16 minus, oh, it's not even worth it, right? 8 minus 8 over 3. Let's see, plus 8 minus another 8 over 3. I'll probably write that as a fraction. Why not? I get 32 over 3. That sounds good to me. And then multiplying that all by 1/4, and you get 8 over 3. So the idea here is, if you graph that function on the interval, maybe we can do that real quickly, since I've got my calculator here anyway. If I graph that function on the interval, so what I've got here is, where's my function? 4 minus x squared. Right, and I graph that. Let me change the window a little bit so we only concentrate on the interval in question. I'm going to go from -2 to 2 in my x values. What's the highest and lowest this function will get? I believe the lowest it'll get is 0, and the highest it'll get is 4. So I'm going to, in my y, maybe I'll go from -1 to 5 just to make sure we can see the whole thing. I'm going to graph that function like this. And the idea here is, on this entire interval, what's the average height of the function? Well, the lowest value is 0. The highest value is 4. What this function is saying, what this answer is saying is, right, 8/3 is the same as what, 2 2/3, right? So it's saying that the average value, if you added up all of the heights here and divided by how many there are, which is impossible because there are infinitely many of them, but if you could do that, then the average height would be 2 2/3. So about right here would be the average height of the function. Keep in mind that means there are more up here than there are than there are at the bottom, right? We're not halfway. We're not at 2, right? Halfway between the maximum and the minimum on this interval, halfway in between those would be 2, but it's actually 2 2/3. So that means that there's more up here than there are down here in this region. That's because of the shape of the parabola, right? It's more dense up here, if you want to think of it that way. Oh, there's lots of ways to think about that. I don't want to confuse you too much. But 8/3 is our nice average height, and that's how we use that mean value theorem to find the average height of a function. Please let me know. Any questions, any comments, any criticisms? I'm here to help.